Chapter 7, Many Worlds, Many Mansions. And here is a quote from Isaac Newton. I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore and diverting myself, and now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me. This is a material world, and I am made of matter, and this matter is made of atoms. Inside each atom, a nucleus. Inside each nucleus, protons, neutrons, pions. Inside these, quarks. Inside these, perhaps yet tinier things. This is a material world, and physics has described it, described the universe, described the matter it is made of, and developed the equations that show how it all fits together and works. With great precision, physicists probe matter to show things as small as 10 to the negative 17th power centimeter and consider times as brief as 10 to the negative 35th of a second. But somewhere along the way, we have passed something by, something that is important. We have to go back. There was something we passed earlier that it seemed for a moment might help us find that something that we now know are missing. There was something about observers, and there was something long ago objecting God does not play dice. The great success of quantum mechanics, of Schrödinger's equation, and Heisenberg's uncertainties, and of all that has been achieved in studying the infinitesimal world of the atom, has lent ever increasing credence to the idea that the wave function actually does describe the real world out there. This wave function, this probability amplitude, really does give us a complete picture and a detailed specification of matter. It describes the complete condition of any collection of objects. Of course, physicists never attempt to write down psi for a whole vista of reality down to its atomic detail. Rather, they try to stick with fairly simple problems. Physicists prefer to break things down into simple pieces, but they also demand of their science that the equations completely describe how things work as assemblages. They want to know fully how things work, understanding the pieces and understanding the whole. Thus, wave function, or psi, which contains pictures of all the potential configurations or states of a system, all the ways a collection of objects can be found to be, describes exactly what the object is, whether atoms or people, quarks or quasars beyond the distant galaxies. This is the complete reality of the system at any moment before it is measured, before it is observed. This wave function is what exists, it is reality. But all this is contrary to the way Albert Einstein conceived reality to be. All of this great accomplishment, all the success of this quantum mechanical conception of nature is the brilliant solution to the wave particle duality problem, wave function being a probability wave describing the chance of finding particles in this or that place, in this or that state of motion. But this very clever solution to the wave particle duality problem has spawned a new and far more perplexing problem that has continued to confound physics. It is a problem that led Einstein to confess, I cannot bear the thought that an electron exposed to a ray of light should by its own free decision choose the moment and the direction in which it wants to jump away. If so, I'd rather be a cobbler or even an employee in a gambling house than a physicist. In this statement, Einstein sounded a discordant note in the quantum symphony even before Heisenberg discovered his matrix mechanics, or Max Born interpreted Schrodinger's wave function as a probability wave. Einstein was to be proved to have been wrong. Einstein was to become, for much of his life, an anachronism swept away by the rapid developments in atomic physics with which he was no longer in tune. And yet, in this, he will probably still prove to have heralded a new vision of reality. Einstein's dissatisfaction with quantum theory, his God does not play dice understanding of reality, is the starting point for a new physics that is only now beginning to appear. Moreover, it is a physics and understanding of reality entirely different from any answer that Einstein ever had in mind, an answer foreign to him and to those who opposed him. Einstein helped to create quantum mechanics and was there during its very inception. But when it finally came to fruition, he, like Schrodinger, turned against quantum mechanics and disavowed what it had become. To understand why Einstein and Schrodinger rejected the quantum mechanical view, we have to understand a bit better just how Einstein pictured reality. And we have to understand what quantum mechanics had become. In order to do this, we must go back in our story and we must go back in time. This next section is called The Battle Lines Are Drawn. By 1920, Einstein had become the world's preeminent physicist. His intuition had painted an entirely new picture of reality, a picture that led him to make the most incredible predictions in the history of science. His momentous predictions were now paying off in experiment after experiment in laboratories around the world. His new theories of relativity rejected Newton's absolute space and time, but Einstein still pictured the universe as a great machine in the hands of a Spinozan god. Einstein pictured space and time as gently curved into a new non Euclidean order where objects traveling on straight line trajectories curl into orbits simulating the effect of gravitational fields of force stretched out across the distances between planets and stars. Objects obey only the law stipulating that they travel along the straightest line that exists for them to travel through this curved space time. Their motions are governed by absolute law. There is for this motion one path and one path only. But physicists peering down into the strange interior world of atomic physics were beginning to see another motion, another behavior, in which the quantum mechanics of probability and chance permitted chaos. Whereas Einstein fashioned a cosmic engine of perfect geometric order, his fellow workers seemed to be saying that God's grand creation has roulettes for wheels and dice for gears, that photons, like bees, buzz where they please. This was not the orderly world Einstein had envisioned. As quantum mechanics developed, everything got worse, at least from Einstein's point of view. What made the whole enterprise so maddening was Bohr's fixation on a literal conception of the probability wave as an absolute descriptor of the world. For Bohr, the fuzzy microworld of the atom was the complete story. Position and momentum were the two key ingredients in Einstein's general relativity, but in quantum mechanics, these two things are no longer mainstays of reality. In quantum mechanics, it is a fundamental principle that we can never know precisely both the position and the momentum of anything. Things are governed by uncertainty relationships that generate probabilistic descriptions of motions. For Bohr, an uncertainty relationship were not just some inability to make accurate measurements, but were the very stuff of reality. For Einstein, if Bohr's arguments were correct, if the Heisenberg uncertainty relations were absolute, then general relativity had to be wrong. As the decades passed, an enormous chasm developed between quantum mechanics and the general relativity of Einstein's creation. General relativity has been eminently successful in describing the universe as a whole, yet it seems entirely inadequate in the microscopic world. Einstein envisioned that all the forces of nature would someday be explained in terms of distortions of space-time, just as he had explained gravitation. But now physicists talk of graviton particles that carry the gravitational force, something totally foreign to Einstein's vision of physical reality. Such an idea is a mockery of Einstein's theory, and if such particles are indeed the carriers of gravity, it is difficult to see how it would be possible to keep Einstein's relativity from falling apart at its base. Is it any wonder that he would have preferred honest labor as a cobbler or even the life of a croupier than to have played the fool as a physicist in the Devil's Casino? In Berlin in April 1920, Einstein and Niels Bohr met for the first time. Planck had invited Bohr to lecture at this German school of physics on his theory of the atom. He had hardly arrived when a lively discussion began between Bohr and Einstein, as R.W. Clark describes it. And this is how it's described. Something was sparked off between Bohr and Einstein at this meeting, the first of a long series of mental collisions whose succession through the years was to have quality quite separate from the impact of genius on genius. For it was Einstein who, 15 years earlier, had first brought an air of unexpected respectability to the idea that light might conceivably consist both of wave and of particle, and to the notion that Planck's quantum theory might be applied not only to radiation but to matter itself. It was Bohr who was to bring scientific plausibility to the first of these ideas with his principle of complementarity, and substance for the second with his explanation of Rutherford's nuclear atom. Yet these very ideas were to create not a unity between the two men, but a chasm. From the early 1920s, as Bohr and those of like mind followed them on to what they saw as inevitable conclusions, Einstein drew back in steady growing disagreement, withdrawing himself from the mainstream of physics and giving to his later years a tragic air which not even the staunchest of his friends could argue away. In order to make this world of wave-particle duality understandable, Bohr invoked a concept he called complementarity. Never mind, said Bohr, that the wave and particle pictures are contradictory. We need them both. These two pictures are complementary to each other. In some experiments, we see photons and electrons as particles. In some, we see only that electrons and photons are waves. The conflict is only in our minds because we attempt to picture the world in terms of everyday images. The answer is simply that when we do an experiment to test for particle characteristics, then that is the behavior matter manifests. When the experiment is designed to show wave properties, that is the behavior that is found. But Einstein did not like this at all. For Einstein, and for me, by the way, physics cannot be right until it is complete and consistent. Bohr was correct to the extent that we should not expect to be able to apply macro world pictures of particles and waves to the atomic world, but we cannot be satisfied to leave physics in a muddle of inconsistencies. Our basic ideas must be logical and complete, and they must fit the equations that so well quantify the physical world. The ideas that Bohr expressed ran counter to all of Einstein's scientific instincts. At the Solvay Congress in 1927, with the greatest array of physicists in the world assembled, the battle flared into the open. In the words of Banish Hoffman, Born and Heisenberg argued that the indeterminacy is unavoidable, that because of the absence of strict causality, the probabilities tell all there is to tell. Bohr agreed, but Einstein did not. He was unwilling to accept what his instinct rejected. He felt that the theory was incomplete, and he brought forth a succession of ingenious arguments in support of his views. Never before had the new quantum mechanics been subjected to so formidable and penetrating an attack. But Bohr and his allies, hard pressed, stood their ground, refining their concepts in the heat of battle. They defeated the objections of Einstein one by one, and Einstein, for all of his ingenuity, had to retreat. The unknowable jolt of observation could not be avoided. On December 12, 1951, Einstein wrote these words to his old friend Michel Bissot. All these 50 years of conscious brooding have brought me no nearer to the answer to the question, what are light quanta? Nowadays, every Tom, Dick, and Harry thinks he knows it, but he is mistaken. Despite Einstein's efforts to prove quantum theory wrong, Bohr's complementarity arguments carried the day. For the most part, Bohr's view of quantum theory is still held by physicists, and yet his ideas are not really theory, but rather a kind of cataloging of experimental results. Certain experiments give particle-like results, some give wave-like results. Certainly, quantum mechanics has worked too well to have been overturned by Einstein's philosophical objections. For the physicist, when the mathematics fits experiments so extremely well, the implications must be accepted. Even though Bohr's complementarity argument surely seemed as much like double talk to many of his fellow physicists at the Fifth Solvay Congress as it did to Einstein, the Schrödinger equation, with Born's probability interpretation and Heisenberg's uncertainty relations, worked. Bohr simply gave physicists a way to keep their minds at peace in this strange new wave particle land. But if Einstein could not prove quantum mechanics wrong, perhaps he could at least show that quantum theory omits fundamental information about reality, information that would have to be present in some future, more nearly complete theory of reality. Perhaps he could demonstrate that quantum mechanics did not prove the basis for a complete understanding of what is real. If Einstein could prove this, prove that the world is not fully described by a probability wave, then someday perhaps someone would be able to penetrate beyond the jitterbug picture of atomic reality. If he could at least show this, then he could make peace with how the world works, even if the final answer eluded him. In 1935, working with Boris Podolsky and Nathan Rosen at Princeton, Einstein thought he finally had what he was looking for. These three published a paper in the Physical Review titled, Can Quantum Mechanical Description of Physical Reality be Considered Complete? This paper was something of a parting shot against quantum theory. After this, Einstein turned his sails to chart different waters, from the rest of the physics community. He would spend the rest of his life searching for his unified field theory, which he hoped would unite his own gravitational theory with all the other forces in nature, and in so doing, yield a physics that would replace quantum theory. He was perhaps searching for some divine certainty in the workings of nature to recapture the logic and order that quantum mechanics and the world had tossed aside. He was not successful in his search, but this parting shot marked the real beginning of a renewed effort to understand quantum mechanics. In the Physical Review article, This Parting Shot, Einstein put his finger on precisely what the issue is. In this paper, Einstein saw the first light of a new understanding of reality, and yet, at the critical moment, he turned back to his earlier belief about what God should do and failed to see what nature is telling us about what God is. The ideas advanced in this now very famous paper by Einstein, Podolsky, and Rosen have come to be known as the EPR paradox. The EPR paradox does not maintain that quantum mechanics is in error, but it tells us just what quantum mechanics is saying about reality, and this is something horrible and wonderful. Note what they say at the outset. In attempting to judge the success of physical theory, we may ask ourselves two questions. Is the theory correct? And two, is the description given by the theory complete? They wish to show that quantum mechanics is incomplete and thus not a correct picture of reality. However, we are looking elsewhere. We are looking for the missing clues to the reality that quantum mechanics omits and that Einstein overlooked. Einstein, Podolsky, and Rosen attempted to prove quantum theory incomplete by proving that there exists properties that properly describe the state of any object, properties that have real values even though quantum mechanics does not ascribe such a reality to these quantities. Thus, Heisenberg's uncertainty relationship says that one cannot measure both an object's position and its momentum precisely and simultaneously. In quantum mechanics, the idea of an object having both an exact location and an exact momentum has no meaning. Either can be measured to any desired precision, but both do not have simultaneous meaning as exact descriptors of an object. We may picture objects located in exact positions with exact motions, but that is not the way reality is described by quantum mechanics. For quantum mechanics, there is a limit on the precision for simultaneously measuring the product of the position and the momentum, a product that has a limit about equal to the value of Planck's constant. Now, if Einstein, Podolsky, and Rosen could show somehow that an object does have a real position and a real momentum, and that both exist at the same time, even though we may be able to measure them, then although quantum mechanics would still describe accurately what we measure in a laboratory, it would not tell us what is real. If this could be proved, then Einstein would be right, and Bohr, who had won the debate at the Solvay Congress, would have been only a clever apologist for a passing fashion in physics. In their 1935 Physical Review article, Einstein, Podolsky, and Rosen considered a system consisting of two particles that are permitted to interact with each other and then separate. During this interaction, the particles share momentum, angular motion, and position. As they separate, they share their total momentum, their angular motion, and a common point of origin. We assume one of the particles stays in the laboratory so that we can measure it anytime we wish, while the other flies out the window and departs to the farthest part of the universe in total isolation. The Schrödinger equation can be used to describe the possible states of these two objects as a result of their original interaction. For example, quantum mechanics can describe for us their exact positions or their exact momenta, but as we already have seen, it cannot give both at the same time for either particle. Now the question is, do these particles really have an exact position and also an exact velocity, which we are unable to measure without disturbing them, or do these quantities not exist as part of reality at all? The usual conclusion in quantum mechanics, Einstein, Podolsky, and Rosen say, is that when the momentum of a particle is known, its coordinate has no physical reality. However, the way quantum mechanics describes how objects behave is very peculiar. It describes reality as a collection of potential realities, a collection of pictures of the world that includes all the things we expect could be found in a measurement. If we call the two particles mentioned above A and B, then quantum mechanics will say there is a series of pictures, mathematical functions, that describe the possible conditions of A and B. This description says that if particle A is given by picture 1, then particle B is given by its picture number 1. If particle A is given by picture 2, then particle B is given by its picture that shows how it moves, and so on. This is because the two particles share all their dynamical properties during their interaction. This means that once we measure the position of particle A, we can use this equation to find out the position of particle B exactly without ever disturbing particle B. And if we decide to measure exactly the momentum of particle A, then we will know the momentum of particle B exactly without ever having disturbed particle B. Thus, Einstein, Podolsky, and Rosen pointed out, by measuring either A or B, we are in a position to predict with certainty and without in any way disturbing the second system, either the value of quantity P, which is momentum, or the value of quantity Q, which is position. Then Einstein and his collaborators made this observation. If without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. This, they believed, proved that both the momentum and the position of both particles A and B have an independent real existence. If the momentum were to be measured on particle A, then we could say exactly what the momentum of particle B was without ever having to measure it. Therefore, B has to have a real momentum. If the position of A were measured here in the laboratory, then the position of particle B, speeding off into the remote universe, would have to have reality also, because we can know all this about particle B without ever disturbing it, and must have both a real position and a real momentum, despite the fact that quantum theory says it does not. Einstein, Podolsky, and Rosen said we are left with two possibilities. First, we can assume that particle B can have a real position or a real momentum because it has such a reality for both position and momentum all the time. This would mean that quantum mechanics is incomplete, just as Einstein had said all along. Or second, we can say that particle B does not have a reality for position or momentum until we have measured the position or the momentum of particle A in the laboratory. Concerning the second alternative, Einstein and company stated that it makes the reality of P momentum or Q position depend upon the process of measurement carried out on the first system, which does not disturb the second in any way. Writing on this same subject 35 years later, C.A. Hooker observed that it is difficult to resist the conclusion that by changing our minds about the measurement to make on one of the systems, we are able to alter the state of the other system. On the one hand, Einstein and his colleagues presented us with the possibility of a rather classical billiard ball reality hidden beyond any reach of experiment, out of view and beyond the realm of knowing the nature of its reality. But on the other hand, if quantum mechanics does describe the true nature of reality, if wave function is the complete representation of reality, then there exists the possibility that a choice made by one's mind, whatever that may prove to be, has an effect on physical events. Could this be what reality actually is? Is it possible that reality is not ultimately a vast collection of overly agitated billiard balls, or even a world of fuzzy hopping and popping atoms and elementary particles? Could it be, instead, that mind actually does affect matter? Could consciousness possibly be a negotiable instrument of reality? With such incredible worlds at his fingertips, Einstein ends this fabulous excursion into the heart of reality with the deflating observation that no reasonable definition of reality could be expected to permit this. Einstein had probed to the very edge of mind, but it was not the world he was looking for, and so he let it slip through his grasp. For the time in which Einstein was writing, when the choice lay between the objective reality he understood and the complementary wave-particle duality doublethink that Bohr would apply to these phenomena, Einstein's choice was a most perceptive indictment of the incomplete vision of reality that Bohr then offered. Bohr's framing of the interpretation of quantum mechanics was still couched in terms of the wave-particle duality problem, a problem that had already been laid to rest by the Schrödinger formulation, but that has lived on for decades in the guise of Bohr's complementarity philosophy. However, Bohr's school of thought, the Copenhagen interpretation, the name refers to the fact that Bohr headed the Institute of Theoretical Physicists in Copenhagen during these years, has evolved in the hands of von Neumann and Wigner into the more mature interpretation. And this refined interpretation enables us to ask the next question in our effort to understand reality, a question that leads us to search for the nature of mind. Einstein, preoccupied with the desire to show that quantum mechanics was incomplete, did not see that the philosophical system, the paradigm on which he had based his physics, was itself hopelessly incomplete. The world we know has conscious observers. The world Einstein described had particles moving along trajectories, but no one to observe. Einstein did what many physicists have done. He assumed that consciousness and mind require no physical explanation. Physics concerns itself with questions about the nature of matter, space, and time, the building blocks of the world. Surely, physicists believe the functioning of the brain is the domain of biology. Biology has to explain how the brain works, and it will have to do that in terms of the physical laws. With such a picture of how mind and reality work, Einstein could avow God does not play dice with the universe, and could believe he had at last proved quantum mechanics to be a flawed picture of reality. But in the worlds that Einstein conceived, there was no place for any such God to exist. This next section is called "The Greater Our Reach, the Less We Grasp." The response to Einstein, Podolsky, and Rosen was neither swift nor particularly insightful. In their answer to the EPR paradox, advocates of quantum mechanics simply held that the representation of a physical system by the wave function does give a complete representation. They said that, paradox or no, there exists no hidden description of an object. The wave function is the full reality of the object. Only by measuring the system can we obtain more information about an object, and not until we make such a measurement will there be any meaning to the idea of exact position or exact speed. Einstein's argument, they maintained, rested only on a philosophical predisposition about what reality is. Thus, the description of anything before measurement is in fact given by wave function. After measurement, the description of the object measured is given by one of the component states, one of the pictures contained in wave function. This is how we use the Schrödinger equation, and it is a natural, factual interpretation of quantum mechanics. This interpretation, which has come to be called the Copenhagen interpretation of quantum mechanics, represents the evolution of Bohr's ideas into a form that finally avoids the language of the old wave particle duality problem. The language frees us of Bohr's complementarity double talk. Yet, despite this progress towards a pragmatic interpretation of quantum mechanics, we do not entirely escape the problems that have beset our efforts to understand the reality that lies behind the practical use of Heisenberg and Schrödinger's quantum theory. It is this understanding of reality, not the practice, that is the use of the equations, that physics is all about. We, as physicists, are trying to find out how nature really works. We can use equations for that description, but the equations must lead not simply to engineering results, but to an internally complete and self-consistent picture of reality. We had thought we had a valid picture of reality in the billiard ball world of Newtonian physics. Quantum mechanics has shown us that such simple pictures are not adequate. Now we have a picture in which the processes in the world, small or large, micro or macro, simple or complex, of few objects or of many, have to be represented by this collection of probabilistic pictures by possibilities. These possibilities, these potentialities, become actualities whenever we carry out a measurement on the system. Such a statement is fine for the laboratory, but we want a description of reality that will work for the everyday world, not just when we are in the laboratory. What does this word measurement mean? Well, it means observation. When we actually observe or interact with any system, then the system goes into one state. Of course, the details of how this happens may not seem important because on the macroscopic level in our everyday world, things work essentially like the Newtonian billiard ball world. For this reason, we can have a practical interpretation of quantum mechanics that says there is a transition, a collapse of the state vector, or in other words, a reduction of the wave function that occurs when we interact with or observe any system. The phrases collapse of the state vector and reduction of the wave function mean that the collection of potential pictures given by wave function becomes or turns into a single state, one of the components or permitted potential conditions of the system. Wave function turns into one of the component states of which wave function consists. A picture of the observed world that we designate by wave function, the subscript I, wave function with an I next to it, the subscript I stands for the number assigned to the picture of reality contained in wave function that actually turns out to be one that happens when we look at the world. But the terms interact and observe are not well defined in physics. One may imagine that the system initially represented by the state vector wave function will, after a time, whirl and grind itself until it finally pops into one of the possible states as a process that happens entirely on its own. But the Schrodinger equation does not tell us this will happen, and it contains no provision for a wave function to change itself into a component state. One might assume that this state vector collapse occurs when we disturb the system by having some measuring device interact with it in order to make a measurement on the system. That is, when the outside world interacts with it. But that is not how quantum mechanics works. When a second system interacts with the first system, all that happens is that we get an even more complicated system with more potential states, a bigger wave function with more little wave function with subscripts, component pictures than before. The measurement device we use to look at quantum mechanical atoms is itself governed by the Schrodinger equation, and therefore it cannot give us anything but a more complicated wave function that is made out of the set of pictures that represent the overall system's potentialities, but now consisting of two parts: one part for the atomic system state in each picture, and one part for the measurement device's corresponding readings. But we do know that when we observe the system, we will see only one picture, one state, one condition. We know that state vector collapse must have already occurred, or that it occurs at the time of this observation. As a result, investigators often speak of state vector collapse on observation, but observation is just a euphemism for consciousness, for mind. This interpretation of quantum mechanics says that the system undergoes state vector collapse because of our mind. Moreover, there appears to be nothing else to blame for state vector collapse. Everything else is something physical, and as a physical system, must be subject to the Schrodinger equation. At best, it can only create more potential states, not remove them. Yet when we observe the system, we know that state vector collapse has occurred. We see only one state, one of the wave functions with the subscript I component states. This effort to obtain an entirely practical interpretation of quantum mechanics, this Copenhagen interpretation, leads us to the incredible conclusion that mind, or consciousness, affects matter. Physicists don't like to fool with biology or philosophy. Something must have gone wrong. Whatever is wrong, that something is called the measurement problem in quantum mechanics. 1,000 physicists have grappled with this problem and failed to come up with any satisfactory answers. They have tried to remove this state vector collapse on observation, this intrusion of mind, into the realm of physics, and they have failed. Einstein was only the first of many to have tried, and yet this is the problem we must solve if we are to peer beyond the veil of the physical world to find the hidden workings of reality. If so many physicists have failed to solve this problem, how can we hope to find the answer? Is there any answer? Perhaps the reason why physicists have failed is that they have believed that they already know how reality works. Believed too much to have paused to hear the message nature has been whispering to them. This is a journal entry. It is January again, January 27th, 1952. I got up at 9 o'clock this morning with 30 cents in hand. I went off to Sunday school and to church. Daddy filled out those NROTC forms. I called Marilyn at 2:45. We talked about nothing till 4. I tried to write a poem to Marilyn to say how much I love her, but the words could not equal what I wanted to say. It has been raining all day, as it is now. Monday, January 28th, 1952. No homeroom teacher. Jimmy Dewberry asked me to collect pennies so he would get class favorite. Miss Borders caught me running in the hall and sent me to Mr. Walker, vice principal, no relation. After school, I gave Marilyn a poem I had written on the 19th, which says that I wish her to be my wife. She later wrote out for me a copy of the poem I had given her, the copy I have now. As poetry, it is awful. Still, it says something that you can only say once in your life in the way it was said and thought. It begins, "My maid holds the balance of my life, and may the day come when she'll be my wife." Incredibly, the thing plumbs still great literary depths. Out of kindness, I spare the reader. On the same day, the 19th, Marilyn had written a poem to me, Questionnaire Solitaire. And this is the poem. I wonder if I love him. Experience has taught me to be cautious. But can you be cautious about love? He is in my dreams, good and bad. I dream that I declare for all to hear, I love you. Perhaps if I knew his heart, I would know better my own. I do not wish to love in vain, yet he does not speak of his heart. So I remain swinging in the balance, first in, then out, love's gate. I do not wish to love him in vain. It would surely break my heart. MZ. I called her when I got home, and later we went to play tennis. Then I went to her house. Tonight I started my new and third book, which will be mainly poetry. P.S. Marlin said to me at her house, Ego te amo. I am all too nondescript lucky to have her. This next section is called Wigner's Friend and a Paradox Box. Whereas Bohr championed the new view of quantum mechanics as a complete yet probabilistic interpretation of physical reality and faced down Einstein's awesome guns, it was von Neumann who revised the conception of quantum mechanics, leaving behind the wave particle duality language and put the interpretation into its modern form. Von Neumann makes clear that there are two ways in which a system described by quantum mechanics can change with time. There is the usual development of a system with time, which lets us take what we know about the motions of an object right now and use that knowledge to extrapolate into the future to find out what the description of the object should be then. And there is a second in which that time can change things. When a measurement occurs, there is a sudden change, a stochastic alteration in wave function that changes it into one of the component pictures. We do not know which picture will occur, but when a measurement happens, when we observe the system, the collection of pictures collapses into one picture, one state. These, then, are the two ways in which things change as time passes. There is no mystery about the first. It is as familiar as Newton's mechanics, with orbits that change the positions of planets as time passes. The only thing new is that there remain all of these possibilities that quantum mechanics allows. The puzzle has to do with the second way things change with time, as that collection of possibilities suddenly changes when we observe what is there. Exactly what causes that sudden change in the description of the system? That is what von Neumann wanted to discover. It is perhaps just that when we make a measurement, we find out what was there all along. Was the result there waiting to be found even before we looked? We will examine this question in much more detail later, but von Neumann gave the first definite answer to the question that Einstein, Podolsky, and Rosen had asked. No, we cannot just treat quantum mechanics as ordinary chance. Quantum mechanics is not just a toss of dice that turns up one of the pictures. No, God is not playing dice with the universe. Something much stranger is going on. But if the object or the system is really described by this series of quantum pictures before measurement, and by a single picture after we actually look at things, then in von Neumann's world, just what physical event triggered the change? Von Neumann tried to answer this question. He used quantum mechanics to follow what happens when we measure something in the real world, following what happens all the way from the material events in the outside world and on into the brain and into the mind. What happens when we try to measure an event, when we try to observe anything? What is it that changes? Schrodinger's equation for these quantum waves of probability tells us that we just get more and more possibilities. But when a message about the results of a measurement travels from the eye down to the optic nerve and into the brain, it becomes a conscious thought somewhere in the brain's functions. When that takes place, then we know the system must be in one single state. Some one thing has had to have happened. Von Neumann does not distinguish well between the brain and the mind, but that does not matter. It is clear that as far as physics is concerned, the brain, though complex, does not have in its chemical processes anything that would alter the results of the Schrodinger equation without changing what the equation itself says. Yet when consciousness enters, everything changes. The physics of Schrodinger, of Heisenberg and Einstein, of Bohr and von Neumann, neither provides any explanation of consciousness nor gives us any place to put it except beyond the edges of quantum theory, where the state vector becomes the picture we see. Von Neumann traces this act of observation back to the very edge of our mind. He illustrates the way quantum theory works by giving specific examples. In one of these examples, the observer is engaged in making a temperature measurement. Here is von Neumann on the way quantum mechanics works. We wish to measure a temperature. If we want, we can say this temperature is measured by the thermometer, but we can carry the calculation further. We can calculate its heating, expansion, and the resultant length of the mercury column, and then say this length is seen by the observer. Going still further and taking the light source and quanta into the eye of the observer, we would say this image is registered by the retina of the observer. And were our physiological knowledge more precise than it is today, we could go still further and then in the end say these chemical changes of his brain cells are perceived by the observer. But in any case, no matter how far we calculate, to the mercury vessel, to the scale of the thermometer, to the retina, or into the brain, at some time we must say, and this is perceived by the observer. The boundary between the two is arbitrary to a very large extent, but this does not change the fact that in each method of description, the boundary must be put somewhere. Indeed, experience only makes statements of this type. An observer has made a certain subjective observation, and never any like this. A physical quantity has a certain value. End of quote. But what justifies putting a boundary anywhere? Eugene Wigner carried von Neumann's analysis one step further into an area called the Wigner's friend paradox in quantum mechanics. He asked what quantum mechanics would say if the observer that von Neumann speaks of should be a friend of his. Wigner's friend conducts an experiment and makes an observation. His friend then comes to Wigner telling him what he has discovered. According to quantum mechanics, should Wigner's friend be treated as merely another step in the sequence of interactions leading to Wigner's knowledge? Question. Should the friend's observation of the measured result be considered just a potential state, or should we, as common sense would suggest, agree that when Wigner's friend observed the result was already in some specific single state. Quantum mechanics cannot give us the answer. Surprisingly, quantum mechanics is incomplete in the face of this obvious consequence of using literally the prescription of the Schrödinger equation. The answer would seem to be that something is wrong with quantum mechanics, that its makeup is incomplete, or that something about the act of conscious observation alters the quantum mechanical description of reality, something that plays a special role in quantum theory. Wigner has seen some of these implications of quantum theory more clearly than most physicists. In his book Symmetries and Reflections, he writes, "It may be premature to believe that the present philosophy of quantum mechanics will remain a permanent feature of future physical theories, but it will remain remarkable, in whatever way our future concepts may develop, that the very study of the external world led to the conclusion that the content of the consciousness is an ultimate reality." And yet, even with such a strong commitment to the idea that consciousness is a part of reality, Wigner does not follow this line of reasoning any further than to say that quantum theory implies its existence. It is not surprising that he falls short of advocating that consciousness is indeed a new entity that exerts a ponderable effect on physical reality. We physicists would do this with only the greatest of reservations, with reluctance, and even with trepidation. Yet it must be considered a clear implication of quantum mechanics to be proved or not. We must answer this piquant question that nature has put to us. But in personally speaking to Wigner about this question of the nature of consciousness, I came away with the impression that he believed consciousness does not govern state vector collapse in quantum mechanics after all, but was itself only one more phenomenology of a complex system, like determining the entire structure of a piece of aluminum. He seems to have acknowledged, but not explored, the possibility that consciousness may play a role in quantum mechanics, and that if so, it will be remarkable. Wigner's position reflects the physicist's desire to obtain a purely physical interpretation of quantum mechanics. Nearly all physicists at some time feel a desire to stand godlike above all creation and view the wheels of nature turn as one would look into the workings of a clock. But even a physicist is not a god, and the equations of quantum mechanics still fall short of perfection. Yet, even in its imperfection, quantum mechanics embodies so much truth that it cannot hide what it omits. Quantum mechanics points to a new path, to an enlarged meaning, to a better physics that must come after, a physics that will be closer to the truth, closer to perfection. Quantum mechanics, even as it stands, inspires us to learn what observation and what consciousness really are. Here's the next little section. I keep looking back, searching like a drifter, collecting pretty pieces of shell and bits of glass from a beach washed well by all of yesterday's waves, looking for memories that have slipped into the quiet past. Occasionally, I hear her voice or catch a glimpse that I had lost and remember the memories from long ago again. Suddenly, I seem to find myself looking up toward the garbage behind her house, and then there I am inside painting a stage prop, a coming out gateway with glittering stars and a shining diamante moon she had designed for her sorority's winter dance at the Pickwick Club, the old Pickwick in Five Points. It is now gone, all of it. The club, the building it was in, the streets. Even the streets are not the same anymore. I hear a memory speaking, teaching. You're painting it too carefully. Don't worry about the details. They won't show when it's on the stage. A memory, a bit of broken glass, a piece of something she said, and I heard something only the two of us ever knew, and only the two of us will ever have known. Then my mind discovers another glittering moment gliding out of the clutter of the busy, empty years since she died. The dance, a night at the Pickwick Club, a night complete with a mirrored ball reflecting pencil beams of color across the floor, streams of light walking across the dancing couples and catching eyes in the dark, glancing, sparkling in the moment's gaiety, pencil beams meeting quickly raised glasses, flashing before climbing up to the ceiling and out into the night. And I was there, fearful of that threatening arena. I avoided the dance floor, afraid of showing my ineptitude out on that foreign terrain, dreading it like the combat zone it was. I was quite terrified of stumbling out onto the dance floor then, and the awkwardness of it all has never left me. But she had taught me at her house and up in the garage the steps that I then knew, and now we danced the steps, dancing to Dancing in the Night, the melody playing in her house and now playing into the night at the Pickwick Club. I look back, looking into the next glinting splinter of glass, and I see the two of us again, a moment frozen in the glaring spotlight as we walk together through the gate we had painted back in the garage behind her house on the mountain amid the longleaf pines, splinters of glass reflecting the colors of my emotions streaming through the rails of that gateless gate. Looking back into my past, trying to find something, we stepped out the back door of the Pickwick, into the alleyway, and into the dark where we could hold each other, kiss, and share a moment of love. Where is that beautiful woman's life now? Where is that soft, warm, loving woman? I look back again, looking into my memory, but if you look too long into a splinter of the past, you will see the sharp edge that cuts. I remember telling Helen, she was sitting in that old 2-story square frame house just off Highland Avenue with its 12-foot ceilings and cubicle rooms. I remember sitting in the kitchen telling my brother's sister in law what had happened. She was a friendly soul with whom I could share my troubled thoughts then. I told her that Marilyn had died. I remember that I smiled. I had seen the same smile on her stepfather's face, too, as he told me about her illness, about the trouble, and now I understood that smile, too. We speak to one another in controlled syllables about things that have come all apart, and pain and horror well up inside to twist our words into grotesque smiles. I was telling Helen, I smiled.